So the last thing that we have to look at in this chapter is titrations. So these are going to be acid-base titrations or base-acid titrations, depending on which direction we're going to go. So I'm sure that you've done this before. You're taking OH minus in the burette and you're adding it to a solution that has H plus in it. As you add it, you see a tinge of pink, right? When you get to the equivalence point, it turns all pink, which means that you have the same amount of H plus as you do OH minus, right? So you've added the exact equivalent amount of OH minus in that solution. A common way to follow these is by pH, and so this would be a solution that is 0.1 of a strong acid HA. And then down here we've got the volume of NaOH added. So let's look at how we might follow this with the addition of NaOH. So if we started off with this 0.025 moles of H3O plus and we added 0.0005 moles of NaOH, we would end up with 0.00200 moles of H3O plus, right? How did we find all this? Well, it's 5 milliliters of 0.1 molar NaOH, and we're given the concentration of H3O plus, and we're given the volume of H3O plus at the beginning. So we just calculated, right, that we had 0.00200 moles of H3O plus left. We know our initial volume from the problem is 0.0250 liters, but we also know that we added 0.00500 liters of NaOH, right? And so our new concentration of H3O plus is 0.0667, and we can convert that to a pH. And here it is on this graph. So we can follow this, we can calculate this, but here's what it's going to look like after each calculation. After adding 10 mils, it's going to be 1.37. After adding 15 mils, 1.60. After 20, it's going to be at 1.95. Okay, at this point, before we talk about excess base, let's talk about where is the equivalence point, right? What is the equivalence point? Well, the equivalence point is where the moles of OH minus equal the moles of H plus. Okay, so we can do a quick calculation. We know the starting moles of H3O plus. We can look at that and compare it to the molarity of NaOH, which we know is 0.100 molar. And if we set that up, we can determine what the volume is of NaOH to reach the exact point where we've added the exact number of moles of OH minus as we had H plus. Okay? So now this is taking us beyond, right? So instead of this 0.00250, now we're adding 0.00300, right? That's more. And so after the addition, we have what's called an excess of NaOH. Okay, so when we consider that excess NaOH, we have a different way of calculating that. Now, what we're doing is we're looking at the pH by saying, okay, that excess was 0.0050 moles. We now put that over the total volume. The starting volume was 25 milliliters of acid. We've already added 30 milliliters of base, and so we've got a total of 55 milliliters. So divide by 0.055 you're going to get the concentration of OH minus. From the concentration of OH minus, you can find the pH of 12. Do that. We can do that for all the rest of these, right? And these points out through here, we're just adding more base, and we're adding more in terms of the total volume, and that's about it. What about this point, right? Well, at the equivalence point, any strong acid, strong base titration, the pH is going to be 7. Here are those pHs for the excess. 35 mils goes up to 12.22, at 40, 12.36, at 50, 12.52. So here's a titration curve, right? It's the one that we just generated. It's 25 mils of this 0.1 molar HCl, a strong acid. It was titrated with NaOH, right? 0.100 molar NaOH. And we know that the equivalence point is 7. Again, that's by definition. So those calculations that we just did follow this, right? We put those in there, and we had those, and we knew that this was going to be 7. So these calculations are relatively simple. Before the equivalence point, you've got a pH, right, that is changing only by the amount of H3O plus. So as the OH minus chews it up, that reduces the amount of H3O plus, and we have to recalculate how much H3O plus there is there. When we get to the equivalence point, you have the exact same of each, and so the pH is 7. After the equivalence point, we're dealing with that excess of OH minus, and so all we have to do is figure out how much excess and how much it's been diluted. Here's the complication in titrations when you have a weak acid by a strong base or a weak base by a strong acid. And that complicates it because the pH is now starting off a little more complicated, right? But this is just x squared over f minus x. We already know that, right? And so the Ka is equal to that, right? This region actually is where you start to create a buffer, right? After you've added some, now you have this weak acid, acetic acid, and acetate ion, right? Its conjugate base. And so we would work with a buffer region here. And then at the equivalence point, what actually happens is you've created acetate. And so now you would use the Kb for acetate, where again, x squared over f minus x, right? And we could figure that one out. And then this one goes back to the previous where it's just excess OH. Right, so here they have it. The initial is the weak acid. Here's the buffer region. Here's the equivalent point with the weak conjugate base. And here's excess OH minus. Didn't import really well, but this is just the opposite, right? Titration of a weak base with a strong acid. And so again, up here, you're going to consider the weak base, right? Kb equals x squared over f minus x. And in here, you're going to have a buffer. Here, you're going to have the opposite now. You're going to be working with the conjugate acid, so Ka is equal to x squared over f minus x. And down here, you're just going to have excess acid. Now, there are a couple of interesting points here. One of them is called the half equivalence point. And at the half equivalence point, the pH is equal to the pKa, and we'll talk a little bit more about why that is. All right, and then the equivalence point again, where it's the weak acid.